folks, so today we're going to be talking about definite integrals. So the idea behind them is we want to find the area under a function. So say we have a function, something like this, something kind of fun, say, and from the interval a to b, okay? And we want to find the area under the graph, okay? So that's all of this guy right here. Okay, cool. What we can do to kind of get an idea of that area is we can draw little rectangles underneath that match up with the function at certain points. Okay. Oopsies. Don't want that guy there. Put there, and there, and there. Okay. And what I did just now, I did a left sum. Okay. So we draw these little rectangles, and you can see when the rectangles get smaller, we'll have a better approximation, and when they're bigger, we'll have a worse approximation. Okay. So all we're really doing here is we're taking our knowledge of geometry, our knowledge of areas, and just adding up a bunch of little areas of these rectangles until we get a decent approximation of our graph, okay? Now remember, there's going to be a certain amount of error that comes with this approximation. So we have these error bounds. Okay, so for our error bounds, most of it is just dependent on the function values and the range of the interval, but then we have this very important letter n here. Okay, and this letter n is how many rectangles you have. A little messy there, but see, for this one we have 7 rectangles, so in this instance n equals 7. Okay, so we actually just did L7 just to kind of keep things straight. So this equation right here will tell us how far off our approximation with summing up our areas is from the actual value. Now you might ask yourself, well, what's the actual value? How do we actually get the actual area under the graph? Well, that is our definite integral right there. Because what this integral is doing is it's summing up really, really tiny areas of rectangles an infinite amount of time. So you have an infinite number of rectangles, and it's summing all of those up over an interval, and we have that in this really nice notation of just a definite integral. Okay, so what we have here is we have, say, ln, and then plus or minus our error bound. So I'm going to denote that as, we'll call that, if I can spell, we'll call that just error, okay? And the same thing would be true if we were doing a right-hand sum. Okay, so you can see that these error bounds are talking about how far off we are from the actual value, because this over here is our exact, and these two are our approximate areas. Okay, very cool, very cool. So that's kind of like just a general recap of what you talked about in lecture and kind of what this section is talking about. So now that we kind of have that groundwork laid out, let's actually look at some problems. Okay, so first and foremost, I just kind of wanted to look at like problems 17 and 18, just kind of generally, mainly so we can get an idea of how to actually draw these rectangles. Okay, So I am doing 17 right now, and this is actually figure A, from your book, if you look in your book. So we are going 1, 2, 3, 4, 5, going up to 5. Oh my goodness, did not make my y-axis big enough, so we're going to go by 2s, 2, 4, 6, 8, 10. And I will label every other one. And same thing down here. Okay, so we have something that looks like we're 1, 1, oops, it's not gonna let me, 1, 1, and we have 4, 8. So those are 2 points we're given. That is our interval, and then our function looks, something a little bit less ugly than that. Something kind of like that. It's not perfect, but you get the idea. And so that is the function we're looking at. And our interval here is 1 to 4. Okay. So this problem is asking for, I'm actually going to put these in 2 different colors. L3 and R3. Okay. So we already saw that that 3, that subscript there, that tells us how many rectangles we have. What that also means is that tells us how wide our rectangles need to be. Okay, so we can get the width of our rectangles by taking our intervals. So let's just do this generally. This right here is the width of our rectangles. Okay, so for this specific problem, we have 4 minus 1 over 3. So we get 3 over 3, so they just have a width of 1. Okay, so now we can actually go in, now that we know the width, we know we need 3 rectangles, we can actually go in and draw them. So let's do L3 first. Okay, so I'm going to color code these purple, L3. So we start at our leftmost value, which is 1. Start at 1 and we go up to the function. Okay, we meet the function. Once we meet the function, we stop and go all the way over for whatever our width is. In this case, 1. So I went up to my function value. This is supposed to be 1 here, and over to 2. Okay, that's my first rectangle. The next one, I start at 2. I go all the way up to meet the function. This is a little wiggly, but you get the idea. And then over and down to 3. Okay, start at 3, go all the way up to meet my function, over and down to 4. Okay, so I have my 3 rectangles right there. And you'll see that when we're doing L3, we leave off the our end value, our rightmost end value. So I didn't start at 4 ever. I started at 1, I started at 2, and I started at 3, but I didn't start at 4. Okay, so what this means is we're going to add up the area of each of these rectangles. Okay, so the area of this first rectangle, well, we know that just has a width of 1. So we're going to have 1 times, but what is our height of this rectangle? Well, to draw this rectangle, we went up to meet the graph. So what that means is the height of this rectangle is the function value at our leftmost value, which was 1. So our height is f of 1. Okay. And then we do our second rectangle, and still we just have a width of 1. And we started at 2, went all the way up to meet the function, and we went over. So our height there is f of 2. And then lastly, same thing for our third rectangle, we get our height is f of 3. Okay, now if you actually look in the book, you'll be able to tell what these values are. My graph does not do a great job of that, so I'm just going to give you what those guys are. So we have 1 plus 5 plus 7. Okay, and then you should get 13. So we have then that our L3 is 13. Awesome, awesome, awesome. Okay, and remember with our L3 with your left, you start at your leftmost value, in this case 1, go up to meet the graph and over, and you should always leave out your rightmost interval and bound when you're doing a left sum. Okay, cool. So now that we have our left sum, we can do our right sum. And I'm just going to go through these generally, just so you guys know how to draw these rectangles and calculate these values. So now with our right sum, I'm going to start at my rightmost value, so now 4. So I'm going to go start at 4, go up to meet the graph, and over. So with the way that I've drawn the graph, you can't tell a massive amount of difference between our third rectangle for our L3 and our first rectangle for R3. But that's just going to happen sometimes, that those match up really closely depending on how the function looks and if you draw your graph well, which I did not. Okay, so we have our first rectangle. Now we want to start at 3, go up to meet the graph, over 1, and down. Okay, and that's our second rectangle. And lastly, we want to start at 2, go up to meet the graph, and over, and down. Okay, and that is our third rectangle. And this time there wasn't any point where we were starting at 1. But we get our areas the exact same way. So our first rectangle still has a width of 1 because this is true for both so this value is true for both L3 and R3. They both have the same width. But now we're going to do times f of 4 plus 1 times f of 3 plus 1 times f of 2. So you see you get a little bit of overlap there when you calculate the two approximations. And so again, I'm going to look at my picture from the book because my graph is actually not awesome. So we have 8 plus, and we already calculated these two, so it is 7 and 5. Whew, mental math. Should get 20. So you can see there's quite a bit of difference between the two, and that's where our error bounds come in. So just for funsies, let's actually, I don't think the problem was asking for this at all. It was not, but let's just calculate our error bounds just so we have a little bit of practice. So our error bounds are the same for L3 and R3. They're the exact same value because if you go back up to your error bound equation, it doesn't depend on whether you're doing L3 or R3. It only depends on your interval and your number of rectangles. Okay, so you have the exact same error bound for both approximations. So let's calculate that right now. So we have f of b minus f of a times b minus a all over n. Remember that b is always your rightmost value of your interval. So you have, up here you have a to b. So b is always your rightmost value and a is your leftmost value when you're looking at the graph. So just kind of keep that in mind. So we have absolute value of f of 4 minus f of 1 times 4 minus 1 all over 3. And if you can remember, we already did this part up here, so we can just plug that number in, which is just 1. Oopsies, don't want to scroll too far. And we also already have f of 4 and f of 1, so we can just plug those numbers in. So we have 8 minus 1 times 1, and so we should get 7. So that means that our actual area is within 7 of both of these values. Okay, so just kind of something to remember. Okay, good. Hopefully everyone is clear at this point how to construct your LN and your RN. Let's go to a different book problem where you're actually given the function, so we can actually calculate some stuff. So let's look at problem 63. I'm going to try to draw this one a lot better. Okay. Not too bad, not too bad. So this function is f of x equals 0.25x squared minus 4. Okay. And we want to approximate the area from 2 to 5 of this function. Okay, and this is that, remember, that is the exact value. So we're going to approximate the exact value. What I'm going to do is I'm going to block off where I'm calculating from. So I'm going to start at 2. So this is 2 right here. I'm going to stop at 5. Just so that I kind of know where my interval lies and how far I need to go. So I realized that I forgot to label these. Ugh, I'm losing my mind in this quarantine, I swear. Okay, very cool. So now we have our interval, we have our graph drawn, we can start drawing rectangles. And so what it tells us to use is L6 and R6 to approximate that guy. Okay. So same as before, let's start with L6 again. So remember, with your left sums, you start with your leftmost value on your interval. So I'm going to start with my 2, and I'm going to go down. In this case, I'm going to go down to meet the function. Okay? And then, geesh, how far over do I go? I forgot to calculate that part. So we have b minus a over n, which is 5 minus 2 over 6. So we get 3 over 6, that's 1/2. So our rectangles need to have a width of 1/2. Okay, so I'm going to go over 1/2. Ooh, tiny, tiny. Okay. Now I'm going to start at 2.5, go up to the graph, go down to the graph, and back down. Start at 3, down to the graph, over 1/2, back down. Start at 3.5, down to meet the graph, over, back up. Okay. But now our function value is 0 at 4. Okay, so what that means is we're going to have a rectangle with a height of 0. Okay, so I'm just going to draw a little line there to kind of remind myself. That rectangle has a height of 0. Now when we go to 4.5, we go up to meet the graph and over 1/2. Okay, so if we count it, 1, 2, 3, 4, 5, ooh, seems like we only have 5 rectangles, we should have 6. Well, remember, this line represents our 6th rectangle. It just has a height of 0. Okay, so now we can actually go through and calculate this value. So our width is going to be 1/2, and our first value is 2. Okay, and then our next one will still have 1/2. They're all always a uniform width. 2.5 plus 1/2 f of 3. I'm going to have to move down here. 1/2 f of 3.5 plus 1/2 f of 4 plus 1/2, oopsies, f of 4.5. Okay, and remember that when we're doing a left sum, we leave out our rightmost value. So now we can clearly see we're adding up the area of 6 rectangles. We have 6 calculations here. Okay, and to get these values, remember that we're just plugging in each of these numbers into this equation. So to get f of 2, we're plugging in 2 into this function, this f of x here that we have. So we have, I'm just going to actually factor out this 1/2 because we're multiplying it by the whole thing, so we can do that. So we have -3 plus a -2.4375 plus a -1.75 plus a Actually, maybe I'll keep it consistent and move this guy down here, plus a negative 0.9375 plus 0, that's our f of 4, plus 1.0625. Okay, and I just got those numbers again by plugging in each of these values into the function here. Okay, and then I'll just tell you what that number is. You get a negative 3.53125, and you can truncate that a lot more than I did. I took it out to 5 decimal places, I guess. Not needed. But if you look at our graph, it actually does make sense, because here we have a lot more of our region that is under our x-axis, which means it has a negative area, and very little that is above our x-axis. So it makes sense that our area would be a negative number. That does make sense. So just kind of fact-checking ourselves, making sure it all adds up. Okay. So that's all that we need to do for L6. Should be sitting pretty good there. So I'm going to move this guy over here. We're ready to do our R6. Okay, now we can draw these rectangles. So now we're going to start at our rightmost value. So 5, go up to meet the graph and over 1/2. We're still going over 1/2 every time. And 4.5 up over. Now when we are at our 4, we're going this way to draw a rectangle. And 3.5 down over, 3 down over, 2.5 down over, and we have our rectangles. So one thing to note here that I didn't up above, but you want to kind of keep track of when you're over or under approximating the area. So see here how our R3s, these pink rectangles, they're over the graph. You know, there's more of the rectangle that's outside of what that area would be. So they are over approximating. When we're looking at L3, these purple rectangles, they are underneath the graph. They're taking up less space than what our actual area would be. So they are under approximating. So maybe I'll add that in here. So these ones are over approximating. And this is under approximating. Okay, and I mean, you can see that from the numbers too. 20 is larger than 13, so obviously 20 is over approximation, whereas 13 is an under approximation, but I wanted to make a note of that. And you can also tell just by looking at a graph if something is going to be, if L3 or if the left or the right is going to be over or under approximating, because concavity and increasing and decreasing can tell you that. In addition, you know, like this problem here, whether or not you're above or below the y-axis. So here, for anything that was under the y-axis, the x-axis, our L6 was over approximating, but over here when we're above the y-axis, our L6 is under approximating. And the opposite is true with our right sums. Okay, so now that we have that figured out, let's go in and let's actually calculate these areas, same as before. So we have 1/2, start at our rightmost value, so that is 5. Okay, and then we're gonna go over to our second one, and I didn't leave myself quite enough space, so I'm only gonna be able to do 2 at a time. So that's 4.5, and then 1/2 f of 4 plus 1/2 f of 3.5 plus 1/2 f of 3 plus 1/2 f of 2.5. Okay, so we have all 6 rectangles. We are golden there. And remember, if you actually did calculate these, we have already calculated these middle 5 values. So that part is done. Really, the only additional part you need to calculate is this f of 5, and then multiply it by 1/2. Okay, so I'm just going to assume that you all are following along and did that already, or maybe just checking answers. So hopefully, if you did all of that, you should get a negative 0.090625. Given that we still have the majority of our rectangles under the x-axis, it still makes sense that we have a negative value. But remember, with our right-hand sums, when we were above the x-axis, we were over-approximating. So those values are going to be more positive. They're going to be larger numbers than for our L6. Whereas when we were under the x-axis, we were under-approximating. So we have less negative numbers to counteract those larger positive numbers. So it makes sense that we're getting a number that's less negative than we were here. Okay. So that's just something to keep in mind. And then the last thing we want to do here is calculate our error bounds. Okay, so error bounds. So we have absolute value of f of b minus f of a times b minus a all over n. Remember, we already calculated b minus a over n. That was 1/2. We did that right here. So that part's already covered. So we can just skip that step. So we have f of 5 minus f of 2 times 1/2, because we already did that step. F of 5 was 2.25, and f of 2 was a -3. So you should get your error bound to be 2.625. Okay, so now that we've done some practice drawing the rectangles, calculating the sums, let's actually look at our error bound a little bit more in depth. And this was actually a problem that was requested, which was awesome. So we're going to look at problem 71. Okay, so you are given the integral from 1 to 3 of x to the x, a weird function, dx, which equals ln plus or minus 0.5. Okay, so what this is telling us is kind of what we saw all the way up here, okay? So it's saying that our exact value is some approximation plus, in this case, our error is 0.5. Okay, so, and we know how to calculate our error bound. So what it's basically saying is that our error bound in this problem is 0.5. And we need to calculate what value of n would give us an error bound of 0.5. So it's basically an algebraic equation. So we have 0.5 equals f of b minus f of a times b minus a over n. But what's our b and a? We weren't given an interval. Well, remember though, we have this definite integral. So this is telling us that our interval is from 1 to 3. What do I say? A to b. So we know what our interval is. So we can say this is f of 3 minus f of 1 times 3 minus 1 all over n, because we don't know what n is. That's what we're trying to calculate. We want to know how many rectangles we'll need to get an error bound of 0.5. That's what this question is basically asking for. How many rectangles do we need to get an error bound of 0.5? Okay, so all that's left to do now is plug in these values into the function and then solve for n. Okay, and the function we're looking at is this x to the x. Not really fun function. So we have 3 cubed minus 1 to the first times 2 over n. Okay, 3 cubed, hopefully maybe you guys know that right off the top of your head, but it is 27, and then just minus 1, 2 over n. And I guess one thing that I should have here is not necessarily strictly equal to 0.5, but we want it less than or equal to 0.5. Okay, so I'm actually just gonna change this right here, because we want an error bound with a maximum of 0.5. Like ideally you want something that has as small an error bound as possible. You want a really small error bound. So we want our max error bound to be 0.5. Okay. So we get 26, and since this is a positive number, I can just drop that absolute value sign, times 2 over n. Okay, I'm going to have to shift down here. Well, 2 times 26, that is 52. 52 over n. And now, remember this is 0.5 over here. Multiply n over here, divide by 0.5, we get n center equal to 52 divided by 0.5. That is equal to 104. Okay, so we have that n has to be greater than or equal to 104. Okay, so we need at least 104 rectangles to have an error of 0.5. That's a lot of rectangles. You would not want to do that by hand. But that's really all this question was asking for, was how many rectangles do you need to get an error bound of maximum 0.5? Okay. So hopefully that cleared up any questions. I've gone through everything that I wanted to, but if you guys do have more questions before you take your quiz, you are more than welcome to email me. I'm always happy to help people out as much as I can. And have a good rest of your day, guys, and good luck on your quiz.